Starting from rest, block A of mass 2 kilograms is pulled along a horizontal table by a force of 15 newtons, which is applied by a light strain that passes over a light frictionless pulley. The coefficients of friction are 0.25 and 0.35. In part A, we're going to draw a free body diagram. So we have the gravitational force and the normal force, since it's on a surface. Those two forces are equal to each other. And then we have the tension force and a friction force. And those two forces, we don't know if they're equal to each other or not right now. In part B, calculate the magnitude of the acceleration of the block. So we know the block is probably going to be accelerating this way, assuming that the tension force is greater than the frictional force, but it's also possible it might not be accelerating or it might be slowing down if the tension force is not bigger than the frictional force. So, first thing we have to do is to see, since the block started from rest, we actually have to see if there was enough tension force to even overcome static friction. So let's figure out what static friction is. The formula for the maximum static frictional force, Ff max, is equal to mu s times the normal force, and since the normal force was equal to the gravitational force, it's mu s mg. The mu s is the bigger of the two coefficients, so we have 0.35, and m is 2, g is 10, so that's 0.35 times 20, which is equal to 7 newtons. So as long as the block is being pulled with at least 7 newtons of force, it will start moving, and you're shown that the block has 15 newtons of force pulling it, so it will move. So we can move on to the rest of part B now and use Newton's second law. The net force in the x direction is equal to the mass times the acceleration, where the net force in the x direction is the tension force minus the frictional force. And now we're talking about kinetic friction, so it's going to be Ft minus mu k mg is equal to ma. Rearrange the equation, just divide both sides by m to solve it for a, and you'll get the answer of 5 meters per second squared. In part C, calculate the speed of the block after it has moved a distance of 50 centimeters. So now we just want to use kinematics. You know the initial velocity of the block, since it started from rest, is 0. The acceleration we just solved for in part B, which was 5. The distance the block moves to delta x is 50 centimeters. Remember, you have to convert that to meters, so 0.5. And you want to get the final speed of the block. When all that is done, you should get an answer of the square root of 5 meters per second, which is about 2.236. In part D, 2 different ways of calculating the block's increase in kinetic energy. Well, one way of doing it is to actually just calculate directly. The increase in kinetic energy, the delta K, is K final minus K initial. And since the block started from rest, the K initial is 0. So it's just equal to the final, which is 1/2 times the mass of the block times V final squared. And we just said that the V final back from over here was equal to the square root of 5. So just plug that in and you'll get the delta K. The other way of showing it is to remember that the work done on the block is equal to the change in kinetic energy. And this is the net work done on the block. That's the work from all the forces. So figure out the work done by tension, which is called Wt, is the force done by tension, the force of tension, times the distance the block moves. The force of tension was 15, and the distance the block moves was the 0.5 meters. So you get a work done by tension of 7.5 joules, but then you also need the work done by friction. And technically you need the work done by the normal force and by the gravitational force also, but those are both 0 since they're perpendicular to the motion. The work done by friction will be negative force of friction times the displacement of the block, and the force of friction, you can plug in the same formula from up here, plug that in right there, and you should get an answer of negative 2.5 joules. So when you add 7.5 and negative 2.5, you get the same answer as you did calculating it this way. In part E, we're going to remove the applied force and now just attach a block B of mass 1.5 kilograms and release it from rest. In parts E and F, we're going to solve these two simultaneously because we're going to end up with two equations and two unknowns. So for block A, the one on the table, if we draw it's going to be the same free body diagram for that block as before. So let's just do a free body diagram now for block B, which is going to be FG, that's going to be for block B. So back on the first free body diagram, I'll call that FG for block A. This one has the tension force going up. Since it said the pulley was lightweight, very light and frictionless, we can say that this FT will be the same as this FT. And for this one, we know that the block is going to be accelerating in the downward direction. So you should set up Newton's second law for the block on the table. That's block A, which is going to look basically like it just did before. You're going to have the Ft minus the mu k mg, only in this case we're going to put mag to make sure we're referring to block A, is equal to mass times acceleration, and again this is ma times acceleration. And then for block B, the hanging block, we'll define downward as the positive direction, since that's the way the acceleration is. So for the downward direction, we have the gravitational force, that's going to be mg, or m, the mass of block B, times g, minus the upward force of tension, is equal to mass of block B times its acceleration. Now we have two equations with two unknowns. The two unknowns are Ft and A. Everything else in both of these equations is known, so you can solve those two equations simultaneously to get the answers to parts E and F. And you'll probably actually find it's easier, slightly easier, to work out part F before part E. If you solve this first equation right here to get Ft by itself and plug that Ft in over here, that'll give you an equation for the acceleration, which is part F. And then once you have that equation for the acceleration, then go back and plug it in to get the Ft. And you'll be getting answers of E, the tension was about 10.7 newtons, and F, the acceleration was about 2.86 meters per second squared. In part G, so using the equation for the gravitational force, m times g, since that mass of the hanging block was 1.5 and g is 10, if you multiply them together, you'll get 15 newtons. That's exactly the same number we had back on the front side of this page for the tension in the string. So if the pulling force back in the first part of the problem was 15 newtons, and this block is basically also has a downward force of 15 newtons, why aren't the accelerations the same? Like back up in the first part, we got an acceleration on the front side of the page. The acceleration was 5 meters per second squared. We got that right here, which we're using kinematics. But now down here in part F, we're getting an acceleration of about 2.86 meters per second squared. So why did the acceleration get so much less? Well, the simple way to explain that is that one way to look at it is that there is now more total force, more total mass in the system. Originally, we just had to have enough force to pull one mass along, the mass on the table. Now we've got force that has to pull two masses along, the mass on the table and the hanging mass. So because there's more mass to pull, it's going to have a lower acceleration. And then finally in part H, if the system is set up in a lab and the acceleration of the block on the table is experimentally determined with a motion sensor, Let's say the experimental value is found to be smaller than the value we got in part F. So we just said the calculated value in part F was 2.86. Let's say we get something like 2.5 meters per second squared. If you know that the given value for the coefficients are correct, and you also know that air resistance is negligible, explain briefly but specifically why the experimental value of the acceleration is smaller. And because this last part is a lab-based question, you could really come up with any answer that is valid. For example, you know now that with a pulley, because it is a rotating object, you were never told the pulley is massless, you were just told that it is light. So the pulley does have some small amount of rotational inertia, which will make the system not accelerate as much. You're also told the string is light, so that means the string does have some amount of mass to it, so that could also be weighing down the system a little bit more. Or you could even come up with something like, for example, you never told the table is perfectly horizontal. What if there's a very slight upward slope to the table that as the block is moving along, it's kind of going uphill, you just don't really notice it? That could also cause an acceleration to be smaller. So as long as you come up with some kind of valid reason, it's an acceptable answer.